Hello dear students, welcome back to the discussions of NCERT line by line questions. Now we discuss the chapter Electromagnetic Induction. One of the very important chapters as far as the history of human beings is concerned. We know in this chapter the concept of electromagnetic induction introduced by one of the greatest experimentalists, Michael Faraday, is discussed. Okay, and its technological exploitation, that is the invention of AC generator by Nikola Tesla. Okay, after which the history of the human beings is entirely changed and there is a surge in the development of humanity. So the chapter is very much important in our development and in this modern era. Okay, so directly we are moving into the questions. Number 1, direction of current induced in a wire by moving it in a uniform magnetic field is found using. When a current is moving in when a wire is moving in a uniform magnetic field, then induced current will be there in the wire. The direction of the current is found by Lenz's law. Okay, the value of EMF induced is found by Faraday's law and the direction is found by Lenz's law. Okay, yes. The next question is, a metallic plate is getting heated. It cannot be due to, what are the options? A direct current passing through the plate. When the current passing through the plate, it may be heated. Okay. Second, an alternating current passing through it. An alternating current also heating the plate. It is placed static in space varying magnetic field but does not vary with time. Okay. It is placed static in space varying magnetic field. Magnetic field is varying according to space. So the plate here is placed at a particular space so that there is the magnetic field constant. It is not varying according to time. So the magnetic field is constant and the plate is stationary there. Then no EMF is induced, no current will be induced, no heating will be there. So the answer is option C. What about D? It is placed in time varying magnetic field. Yeah. If the plate is placed in time varying magnetic field, EMF will be induced, current will be induced, heating will be there. Okay. So the answer is option C. Good. The next one. A rectangular coil expands on pulling from two diagonal edges in a region of magnetic field and no EMF is induced in the coil. This can be because of a rectangular coil expands from two diagonal edges, pulling from two diagonal edges, it expands in a region of magnetic field. This region of magnetic field may be directed into the plane or it may be out of the plane. Okay, maybe. This is a region of magnetic field region and there is a rectangular coil. It is expanding, but no EMF is induced. Okay, this can be because of option A. Magnetic field is constant. Magnetic field is constant, but area is changed. Okay, then EMF will be induced. So this is not the answer. Okay, B. Magnetic field is in the plane of rectangular coil. Magnetic field is along the plane of the rectangular coil. That is the answer. What about the magnetic flux phi? Magnetic flux phi is equal to vector B dot vector A. This is equal to BA cos theta. Okay, the angle theta is between vector B and vector A. Vector A is perpendicular to the plane. Okay, perpendicular to the plane means as per this figure, vector A is directed into the plane, perpendicular to the plane, and the field is also directed into. Then what is theta? In this case, 0. Then cos 0 is 1 and the flux is maximum now. Okay, and now if the field is parallel to the plane of the coil like this, if the field lines are parallel to the plane of the coil, what is the angle between vector B and vector A? Vector A is perpendicular to the plane and vector B is in this direction. The angle is 90 degree. Cos 90 is 0. Flux is 0. Flux is 0. Okay, no flux is there. Now in this case, there won't be any change in flux. Then no EMF will be induced. Okay, magnetic field is in the plane of the rectangular coil is the answer of the question. Clear? Now, magnetic field has a perpendicular component to the plane of coil whose magnitude is decreasing. In that case, flux will be changing and EMF will be inducing. There is a uniform magnetic field perpendicular to the plane of the coil. A uniform magnetic field is there perpendicular to the plane of the coil and the area is increasing. Then flux will be changing and EMF will be inducing. So in all these three cases, EMF will be there, but in this case B, no EMF will be induced. Understood? Okay. The next one. The self-inductance L of a solenoid of length L and area of cross-section A with a fixed number of turns per unit length increases as. We know self-inductance L of a solenoid is mu 0 n square, then area, then length of the solenoid. This formula we have derived. Mu 0 n square area into length of the solenoid. Okay, this increases as, self-inductance increases as. When this value is increased, option A, L and A increases. L and A increases means self-inductance will be increasing. First option is correct answer. Okay, L decreases and A increases. Okay, L is decreasing and A is increasing. Okay, then this may be kept constant. Clear? Both L and A decreases, then this inductance will be decreasing. Okay, L increases and A decreases, then the similar case here also this may be constant. Okay, so if both of these quantities are increasing, definitely self-inductance will be increasing. Clear? Yes. Question number 5. The mutual inductance of a pair of coaxial neighboring coils. Mutual inductance of a pair of coaxial neighboring coils. Okay, let this be the outer coil and considering an inner coil, which are coaxial. Okay, having the same axis for both of them. Then what about the mutual inductance? Mutual inductance M is equal to mu 0 n1 into n2 then pi into r square into length. Let this be the length of the two coils. This pi r square is the cross-sectional area of the inner coil. Then this is the formula for mutual inductance. We studied it. Right. Options. Increases when they are brought nearer. These are already very nearer. Okay, then this is the formula. No change in this case. Right. Then B. Increases when one of them is rotated about an axis. One of them is rotated about an axis. No change in the mutual inductance. C. Is independent of current passing through coils. No current is here in this formula. So this is independent of the current passing through the coil. Option C is our answer. Both A and Z are correct. No, A is not here in the picture. So the answer is C. Understood? Okay. Next, 6th. A square loop of side length L lies in xy plane in a region where the magnetic field is given by vector B is equal to B naught into I cap plus 2j cap plus 3k cap. B naught is positive constant. The magnitude of magnetic flux passing through the square is. Okay, we are having the coordinate system like this. Suppose the origin x, y, z. Okay, this is the positive z-axis, right? Then the square loop of side L is placed in the xy plane. It is placed in the xy plane. Yes. Okay, side length is L, placed in the xy plane. Okay, now here is a magnetic field intensity in this region. The field intensity has components along x, y and z. B naught I cap along x, 2 B naught J cap along y, and 3 B naught K cap along z axis. Okay, we are having the equation of flux. Magnetic flux is equal to vector B dot vector A. Okay, since this plane is in the xy plane, its area vector is along z-axis. Okay, xy plane. Then perpendicular to the plane is in this direction. This is along z-axis. Okay, yes, yes. Then we have its expansion as bx ax plus by ay plus bz az. Okay, the expansion of a dot product. Okay, here ay and az are zeros because the area vector is only along z direction. So ax and ay are zeros. Okay, there is no component along x direction for area vector and also along y direction. The only area vector is along z direction. So these two terms are zeros. And bz is, what is bz is b naught into 3. 3 b naught into area vector is L square. Area vector is L square. Understood? So the answer is 3b naught into L square. Where is it? 3b naught into L square, option B. And the SI unit is Weber. The SI unit of magnetic flux is Weber. Fine. Okay. The next one. A 20 centimeter long conductor carrying a current of 10 ampere is kept perpendicular to magnetic field of 0.6 Tesla. Okay. The mechanical power required to move the conductor with a speed of 1 meter per second is. Okay. The length of the conductor is 20 centimeter. Let this be the conductor having length 20 centimeter. Good. 10 ampere current is passing through it. It carries of 10 ampere current. Good. It is kept in a perpendicular magnetic field of 0.6 Tesla. Let this be the direction of magnetic field directed into the plane and the amount is 0.6 Tesla. Okay. The mechanical power required to move the conductor with a speed of 1 meter per second is. Okay. Suppose it is moving in this direction with a velocity 1 meter per second. Okay. Then EMF will be inducing. EMF will be inducing across its ends. Clear? Then we have the equation of power is equal to voltage into current. There is formula. Okay. Electrical power. Okay. I square R is there. Okay. V square by R is there. Then VI is there. V is this one EMF. Okay. What is the induced EMF is BLV. The motional EMF is BLV. All the values are given. B is equal to 0.6. The length is 20 centimeter. The speed is 1 meter per second. Current passing is 10. Okay. Yes. This 0 and this 0 cancelled with 10 power minus 2. 100 into 10 power minus 2 cancelled. 2 into 0.6 that is 1.2. Okay, 1.2 and the SI unit of power we know watt. The answer is option A. Clear? Yes. The next one, a square loop of edge 20 centimeter and resistance of 1 ohm is placed vertically in horizontal plane. Horizontal plane. Considering this as the horizontal plane, suppose. Horizontal plane. Okay, and it is a square loop whose edge is 20 centimeter. 20 centimeter. Resistance of this square loop is 1 ohm. Resistance of the square loop is 1 ohm. Okay. Is placed vertically in a horizontal plane. Oh, okay. This is placed, not placed horizontally. This is placed vertically. This is placed vertically. The square loop is placed vertically. Okay. Like this. Okay. This is having 20 centimeter length and the resistance of this total wire is 1 ohm. 1 ohm. Okay. Placed vertically in a horizontal plane. This is horizontal plane and this is placed vertically. Good. A uniform magnetic field of 0.5 Tesla is set up across the plane in the direction at 45 degree to the plane. Okay. Let this be the horizontal direction. Then the field intensity directed at an angle of 45 degree. Okay. Yes. 45 degree to the plane. Okay. 45 degree to the plane. Yes. And how much value is 0.5 Tesla field intensity? Good. The magnetic field is decreased to 0 in 0.2 seconds. Okay. The change in magnetic field intensity, delta B, the magnitude of change, the magnitude of the change in the field intensity is from 0.5 Tesla to 0. 0.5 Tesla to 0. So the change is 0.5 Tesla magnitude. 0.5 to 0 means the change is 0.5. Okay. It happens in what time? In 0.2 second. This change in field intensity happening in 0.2 second. Okay. At a steady rate. Good. Calculate magnitude of current induced in this time interval. The current induced is EMF divided by resistance. EMF divided by resistance. And the EMF is equal to flux change divided by time interval. The rate of change of flux, that is the average value of induced EMF. Okay. Divided by resistance. Clear. We have the formula of magnetic flux is B dot A, that is BA cos theta. BA cos theta. Okay. In this formula here A and cos theta are fixed. Which is changing? B only changing. Okay. So what is delta phi is equal to A into cos theta into delta B. Understood? A into cos theta into delta B. Clear. So delta phi is equal to A. What about the area? 20 centimeter square. Okay. 20 centimeter square. That is 400 into 10 power minus 4. Okay. Then cos theta. Cos theta is cos 45. That is 1 by root 2. Clear. Then delta B. Delta B is 0.5. Okay. This much is delta phi. Divided by delta T. Delta T is 0.2. Okay. And in the denominator there is resistance 2. The resistance value is 1. Okay. This much is the current. Okay. We can calculate. 0.5. 0.5 is 1 by 2. Okay. 1 by 2. 2 into 2 here 4. 0.4. 2 into 0.2 is 0.4. 0.4. Okay. That is 4 into 10 raised to minus 1. Okay. 4 cancel. Okay. Here 100 remains. Okay. 10 raised to minus 4 divided by 10 raised to minus 1 is 10 raised to minus 3. Okay. And there is 100. 100 into 10 raised to minus 3 is 10 raised to minus 1. Okay. So 10 raised to minus 1 divided by root 2. Okay, 10 raised to minus 1 divided by root 2 is the answer. I am writing here that answer is 10 raised to minus 1 divided by root 2. Understood? 1 by 2, 2 into 0.2, that is 0.4, that is 4 into 10 raised to minus 1, 4 cancel, 10 raised to minus 4 by 10 raised to minus 1 is 10 raised to minus 3, into 10 raised to, that is 10 raised to minus 1, divided by root 2. Okay, what is root 2 is 1.41. Okay, 1 divided by 1.41 into 10 raised to minus 1. Clear? And here in the options there are milli. Okay, then we multiply this with 10 raised to 2, then this one with 10 raised to minus 2, then this totally will be milli. Okay, then this is 100 by 1.41. 100 divided by 1.41. 100 divided by 1.41 milliampere. 100 divided by 1.41 milliampere. Okay. So the answer is 70 milliampere. Isn't it? 100 divided by 1.41 milliampere, approximately 70 milliampere is the answer of the question. Understood? Clearly? Okay. Good. The next one. A circular loop with its plane parallel to plane of paper is entering into uniform magnetic field directed into the plane of paper perpendicularly. Circular loop is there with its plane parallel to plane of paper. Let this be the paper. Okay. And there is a circular plane. Okay. Okay. This is the paper and this is a circular plane. Okay. Yes. Now, entering into, okay, this circular loop is entering into a uniform magnetic field directed into the plane of the paper. Plane of the paper perpendicularly. So, the magnetic field intensity directed perpendicularly. Like this, suppose. Okay, this is the plane of the paper and the field lines are directing perpendicular to the plane of the paper. Okay, and a circular coil is entering into this region. Understood? Into this region. Okay, if it is entering into the region, some of the areas are passing to the field region, so that EMF will be inducing. And as the coil moves forward, more area is covering, so that the induced EMF goes on increasing. Induced EMF goes on increasing. Okay. And once the entire coil is entered into the region, thereafter no EMF is induced because further no change in the flux. Okay. You imagine. Okay. If it is moving with a constant velocity, it is entering. So EMF starts to induce. It is increasing. And after it is completely ended, then and moving with a constant velocity, further no EMF. Because no change in flux. Understood clearly? Yes. Then now no EMF will be induced in the coil. That is wrong. Induced EMF is constant in magnitude only. That is wrong. Induced EMF is varying with the time. It is varying initially. Induced EMF is constant in magnitude. That is wrong. So the answer is option C. Clear? Okay, the next one. A metallic rod of length 20 centimeter is rotated with a frequency of 50 revolutions per second, with one end pivoted at the center and the other end at circumference of circular metallic ring of radius 20 centimeter. Okay. First of all, I am drawing a circular metallic ring, okay, whose radius is 20 centimeter. So, one end of this metallic rod is at the center and the other end is on the circumference, like this. This is the metallic rod. This yellow one is the metallic rod and this is a circular frame. Okay, yes. Now, it is rotating. with a frequency of 50 revolutions per second. That is also called hertz. Yes. Okay. The length of the rod is 20 centimeter. That is the radius of the circle is 20 centimeter. Okay. Now, this rotation is about an axis passing through center and perpendicular to plane of the ring. Yes. The rotation is based on this axis. Yes. This is the rotation. So that is based on this axis, this axis. Good. A constant and uniform magnetic field 1.5 Tesla parallel to axis is present everywhere. Parallel to axis, this is axis, and parallel to axis may be into the plane or it can be out of the plane. In both situations, it's okay. Parallel to the axis. Okay, now I'm drawing into the plane. Good. What is EMF induced between center and periphery of circular ring? What is the EMF induced between these 2 points? The rotational EMF is studied in this situation directly derived in NCERT. Okay, the rotational EMF is half into B R square omega. Half into B R square omega. This is the equation. Okay, half into field intensity 1.5, that is 3/2. Okay, radius is 20 centimeter. Its square is 400 into 10 raised to minus 4. Omega is 2 pi nu, right? Omega is 2 pi nu. Okay. 2 pi into nu value is 50. Hertz is the SI unit. Okay. Yes. This is to be calculated. Yes. This is 3/2. 2 into 2, 4. 4 cut. Then this is 3 here. Okay, then 10 raised to 2, 10 raised to minus 4, that is 10 raised to minus 2, 10 raised to minus 2. Okay, 2 into 50, that is 100. So 10 raised to minus 2 and 100 cancelled. The remaining is pi. I think you understood it. Okay, 3 pi is 9.4. 9.4 volt. Clear? Calculation is very simple. Okay. Moving to the next one. A cycle wheel with 20 metallic spokes, each 1 meter long, is rotated with the speed of 60 rad per second. 60 rad per second means angular speed. Omega of the rotation of the cycle wheel is 60 rad per second. Yes. In a plane normal to horizontal component of Earth's magnetic field. Okay. Suppose the horizontal component of Earth's magnetic field is directed in this direction. Then the cycle wheel is rotating in a plane perpendicular to this one. Horizontal component is directed in this direction, suppose. Then the cycle wheel is rotating in this plane. This plane is perpendicular to this. Okay. So the cycle wheel is rotated in this plane. Okay. And the cycle wheel has 20 metallic spokes. Okay. Totally there are 20 spokes are there. Okay. I am not drawing completely. Totally there are 20 spokes. Okay. Now what? BH value is 0.5 Gauss. BH value is 0.5 Gauss. Gauss means 10 raised to minus 4 Tesla. Good. Okay. The EMF induced between the axle and rim of the wheel is. Okay. Here between the axle passing through the center and the rim of the wheel is. You know, EMF will be induced across each and every spoke. And that value is equal to written in the earlier question half into BR square omega. Okay. Across each and every spoke. This is one spoke, then another one, then another one, in that way. Okay. This is the point through which the axle passing, and this is the circumference. Okay. Yes. Like this. This is the rotation. Okay. Rotation. Okay. Now, EMF will be induced across the ends of this spoke, and it is half BR square omega. Okay, and there are 20 such spokes in total. Okay, but the EMF across each spoke will be same. Okay, the potential of this point and this point is same, which means all the 20 spokes are connected in parallel. You understood? All the 20 spokes are connected in parallel between this potential point and this potential point. This potential point is similar across the circumference. This potential point is at the center. Okay, so all are connected parallelly. Okay, so we will have only one value. What is the potential difference across the center and the circumference? This only. This only. Okay. Okay. Doesn't matter how many spokes are there. Yes. So this is the answer, half into. Now B value is 0.5 into 10 raised to minus 4. Good. Radius is, how much is the radius? Each 1 meter long. Okay. Each spoke is of 1 meter long. So that is the radius. 1 square. Good. Okay. And the omega value 60 is given. Omega value 60 is given. Okay. Yes. Half into B into R square into omega. Okay. This is equal to 1 by 2, 1 by 2, that is 1 by 4. 60 by 4. 60 by 4 is how much? 60 by 4 is 1, then 20, that is 15. Okay. 15 into 10 raised to minus 4. Check the values. Okay. That is 1.5 into 10 raised to minus 3. That is 1.5 millivolt. Okay. 1.5 millivolt is the answer of the question. You understood? Okay. Okay. The next question is, a conducting arm AB of length 30 cm moves on conducting rails held parallel. Okay. There are conducting rails. Okay. On these rails, a conducting arm AB of length 30 cm is moving. Conducting arm of length AB. Let this be a conducting arm whose length is 30 cm. 30 centimeter. Okay. Clear? It is moving in a uniform, see, is moving on these conducting rails. Okay. A uniform magnetic field of B is equal to 0.2 Tesla. This is B. Okay. 0.2 Tesla exists perpendicular to planes of the rails. In this region, there is a perpendicular field. Okay. Let it be into the plane of the board like this. Okay. The value of the field is equal to 0.2 Tesla. Good. Only the conducting arm has resistance of 0.5 ohm. This AB has resistance given 0.5 ohm is the resistance of this conducting arm AB. Okay. The arm is pulled out with a constant speed of 20 meters per second. This is moving with a constant speed of 20 meters per second. Okay. How much force is required parallel to rails to keep it moving at same speed? How much force we need to apply for this conducting arm keep moving with this speed? Okay, we need to get the force. How much force is required? Clear? See here, a current is passing through it. Clear? Due to the passage of current, the force acting on the conductor F is equal to I into L cross B. We studied it. The force. The force acting on a conducting rod in a uniform magnetic field, F is equal to IL cross B. IL cross B. IL cross B. That is ILB sine theta. Here, angle theta between the direction of current and field intensity. The field intensity directed into the plane and the current is directed in this way, suppose. Okay. Okay. What will be the direction of current? We will get the direction of current through it. See, this acts as a cell. If it is moving in this direction, then the positive polarity or the higher potential will be along the direction of V cross B. V cross B, along the direction of V cross B. Velocity in this direction, B into the plane, then V cross B is upward. From V to B, we have to curl the fingers. Then V cross B is directed upward. So point B is at higher potential and point A is at lower potential. Now this acts as a cell. Which one? AB acts as a cell. Clear? Then within the cell, what will be the direction of the current? Within the cell, the direction of the current is from negative polarity to positive polarity. Isn't it? Suppose we are having a cell and is connected to an external resistor. Clear? Then within the cell, the current is in this direction. So within the cell, the current is from negative electrode to positive electrode. Okay, means the current is directed from A to B. Current is directed from A to B in this particular case. Okay, so the direction of current and field intensity are perpendicular to each other. Theta is equal to 90 degree, sin 90 is equal to 1. So the force experienced by the conductor is maximum ILB. ILB. And what will be the direction of this force? The direction of this force is along IL cross B. IL cross B. What is the direction of IL? That's the direction of current upward. Okay. Then field intensity into the plane. Okay. IL is upward, field intensity into the plane. We are curling the fingers of right hand. Thumb is indicating leftwards. That's the direction of this force. Okay. So due to the flow of current, the force acting on AB is towards left. Okay. Yes. To move the conductor with a constant velocity to rightwards, the net force on it should be 0. The net force on it should be 0. Then only the motion becomes uniform motion. Okay. Means we have to apply equal and opposite force in the forward direction. The external agent has to apply equal and opposite force in the forward direction. Then only the speed of the rail becomes constant. Understood? Means we need to apply a force which is equal to this much amount in this direction, ILB. So we have to calculate this one. Clear? And what about current is EMF divided by resistance. Okay. Then length of the road, then field intensity. Okay. Resistance is given 0.5 ohm. Okay. And what is the EMF? Motional EMF, that is BLV. Motional EMF is BLV, isn't it? Motional EMF is BLV divided by resistance, okay, into length L into B. Now we need to put the values. Clear? B value, B is 0.2. B into B. 0.2 is 2 into 10 power minus 1. Square of that value is 4 into 10 power minus 2. 4 into 10 power minus 2. Okay. Length into length. Length is equal to 30 centimeter. 30 centimeter is what? 3 into 10 power minus 1. 30 centimeter, you know. 30 into 10 power minus 2. That is 3 into 10 power minus 1. Square it. That is 9 into 10 power minus 2. 9 into 10 power minus 2. Okay. Into velocity. You know. Velocity means that speed is 20. Speed is 20. Yes. Divided by resistance is 0.5. 0.5 is 1 by 2. 2 to the numerator. 2 to the numerator. So we get 10 power minus 2 into 10 power minus 2 is 10 power minus 4 into 10. That is 10 power minus 3. Clear? Then this 2, then 4. 2 into 4, 8. 8 into 9. 8 into 9, that is 72. 72 into 2, that is 144. Okay, 144 into 10 power minus 2. 144 into 10 power minus 2. That's equal to 144 into 10 power minus 2. See, 144 into 10 power minus 2 Newton. I think this is 1.4 Newton. Clear? 1.4 Newton. We need to check once again. This is 10 power minus 2 into 10 power minus 2, that is 10 power minus 4 into 10, that is 10 power minus 3. 10 power minus 3 into 144. 10 power minus 3 into 144. So the answer is 0.14 Newton. 0.14 Newton. I think you understood it clearly. Okay? Yeah. Moving to the next one. Which statement regarding eddy currents among the following is incorrect? Incorrect. If rectangular slots are made in copper plate, the magnitude of eddy currents will decrease. This is correct. Okay, magnitude of eddy current we can reduce by putting the rectangular slots. Dissipation of heat produced is proportional to strength of eddy current. Yeah, if eddy current is greater, then the heat produced also will be greater. Deadbeat galvanometer has fixed core made of non-magnetic metallic material. Non-magnetic. This is to be focused. Okay. What about the fourth one? Magnetic brakes in train use the application of eddy current. This is true. Fourth one is true. C is incorrect. So that is our answer. See here. Deadbeat galvanometer has fixed core made of magnetic metallic material. Then only eddy current will be formed and the damping is taking place. Okay. Then only. That's why this is the incorrect statement and that's the answer of the question. 14th, two circular coils, one of small radius r and other of larger radius r. Smaller radius is much less than the larger one. Are placed coaxially with the centers coinciding. Okay, coaxially. The mutual inductance of the arrangement is. Okay, let's check. This is a smaller one and this is a larger one. Okay, yes. This is having radius small r and this one radius capital R. Okay, the mutual inductance of this system is what? Consider current. We are considering the current flowing through the outer coil. Okay, the current flowing through the outer coil. It produces a magnetic field intensity at the center. The magnetic field intensity produced by this current at the center is mu 0 I divided by 2a. 2a. A, you studied it. Mu 0 I divided by 2 into radius. Okay. The field intensity at the center of a circular current carrying loop is mu 0 I divided by twice of the radius. Okay. This field intensity is filled almost throughout the area of this inner coil. Okay. Yeah. Hence, there will be flux along this inner coil. There will be magnetic flux along this inner coil. Okay. So, the magnetic flux of the smaller coil is directly proportional to the current passing through the outer coil or larger coil. That is the mutual inductance. Okay, the flux of one depending on the current of the other, that is the mutual. Okay, so that is mutual inductance. The flux through this one inner one depends on the current through the outer one. Okay, and the proportionality constant is called mutual inductance. Clear? So what about the mutual inductance? M is equal to flux through the smaller coil divided by the current through the outer coil. That's it. Yeah. And what is the equation of flux is B dot A. B dot A. The dot product of the field intensity and area vector. Okay. Yeah. The field intensity along the area of the smaller coil is mu 0 I divided by 2R. Mu 0 I divided by 2R. Into area. Area of the smaller coil is pi R square. Pi R square. Divided by the current I here. Okay. So phi s is B dot A. BA cos theta. Cos theta is 1 here because field intensity in this direction. In this direction. And also the area vector also perpendicular to the surface in the same direction. Theta is 0. Cos 0 is 1. Okay. B dot A is BA. Okay. The I is cancelled. Clear. We get mu 0 pi R square divided by twice of the outer radius. Okay, yeah, mu 0 pi r square divided by twice of the outer radius. That is option B is the correct answer. Understood clearly? Okay, the next one. A long solenoid is of length 1.25 meter and 600 turns per unit length. A solenoid has number of turns per unit length is 600 meter inverse. Okay. It is connected to a source which establishes a current of 2 ampere. 2 ampere. The current passing through the solenoid is 2 ampere. Magnetic energy stored in the solenoid coil with cross-sectional area 0.1 meter square is. Okay. Area of cross-section of the solenoid is 0.1 meter square. Okay. The length of the solenoid is given 1.25 meter. It's a very long solenoid. Okay. The magnetic energy stored by the solenoid is U is equal to half into Li square. Half into self-inductance L into current square. Okay. Yeah. And what is the self-inductance value of a solenoid is mu 0 N square, then cross-sectional area, then length. This is self-inductance. Studied it. Mu 0 N square, then area into length of the solenoid into current square. Yeah. This is equal to half into putting the values. What is mu 0? Mu 0 is 4 pi into 10 power minus 7. Okay. Number density is 600. 6 into 10 power 2. 6 into 10 power 2. Square it. 36 into 10 power 4. 36 into 10 power 4. Cross-sectional area is 0.1. Okay. Length of the solenoid is 1.25. 1.25 is 5 by 4. 5 by 4. Can we write it so? Yes, we can. 5 by 4. Then we can cut this 4. That's fine. Say length is equal to 5 divided by 4 meter. Yes. Okay. Now current square. Current is 2 ampere. Square is 4. Yes. 4 by 4 is cut. Okay. 4 by 2 is 2 pi. Okay. 2 pi. Yes. 2 pi into 36 into 5. Okay. 4 and 4 cut. Now 0.1 into 10 power 4 is 10 power 3. 10 power 3 into 10 power minus 7 is 10 power minus 4. 10 raised to minus 4. Clear? Yes. 2 into 5 is 10. 10 into 10 power minus 4 is 10 power minus 3. Okay. 36 pi into 10 raised to minus 3. Isn't it? 36 pi into 10 raised to minus 3. Okay. Pi is 3.14. 36 into 3 is more than 108. So around 110. 110 into 10 power minus 3. What is the value? 110 into 10 power minus 3. Our answer is option A. 110 into 10 power minus 3. Okay. Shifting to 3 decimal place to the left. 0.11 joule is the answer of the question. Understood clearly? Okay. Yeah. The next one. A rectangular coil of 100 turns with area 0.1 meter square. The number of turns of the rectangular coil is 100. Cross-sectional area of each turn is 0.1 meter square. Okay. Is rotated at 10 revolutions per second. The number of revolutions per second is called frequency of rotation. Isn't it? Frequency nu. So this is nu is equal to 10 revolutions per second. That is also called hertz, the SI unit. Hertz or RPS. Hertz. Both are same. Okay. And placed in a uniform magnetic field of 0.01 Tesla. The rectangular coil is placed in a magnetic field of 0.01 Tesla. Perpendicular to the axis of rotation of the coil. Okay. The coil is here. Perpendicular to the axis of rotation of the coil. See, let this be the axis of rotation of the coil. Then perpendicular to this one, the field is set. Okay, magnetic field intensity is set like this into the plane. Suppose Okay, axo-rotation of the coil. Field intensity directed into the plane. And here is the plane rotating like this. Right. Okay. The maximum voltage generated in the coil is, the maximum voltage generated is an alternating voltage. An alternating voltage E is equal to E max then sin omega t. This is the alternating voltage. And the maximum value E max is NBA omega. NBA omega. We have derived the result. You studied it. NBA omega. The maximum EMF generated in the coil is number of turns, field intensity, area, then omega. What about omega? 2 pi nu. 2 pi nu. Omega is equal to 2 pi into frequency. Okay. Now putting the values. Number of turns 100. Field intensity value is 0.01. Okay. Then this becomes 1. 100 into 0.01 becomes 1. Okay. Area of cross section is 0.1. Okay. Omega is 2 pi into frequency. Frequency is 10. Frequency is 10. Okay. 100 into 0.01, that is 1. 0.1 into 10, that is 1. Into 2 pi. Okay. 2 into pi, 6.28 volt. Correct. 2 pi voltage, 6.28 volt is the answer of the question. Okay. Yeah. The next one, 17th. Two thin cylindrical pipes of equal internal diameters made of aluminum and plastic are taken. One is made of aluminum, second one plastic. Okay. The pipes are kept vertical. Okay. One made of aluminum. Okay. This is of material aluminum. And the other one of same diameter. This is of plastic. Okay. Kept vertical as shown. A small cylindrical magnet without touching sides of wall of pipe is allowed to fall one by one. A cylindrical magnet is allowed to fall. Okay. North pole, south pole. Suppose a cylindrical magnet is just placed or it is just dropped. It allowed to fall through these cylindrical pipes. Okay. Then correct observations are, see, aluminum is a magnetic material, it's paramagnetic. While this is falling down, there will be energy wastage in the form of eddy current. In the form of eddy current, there will be energy wastage. While this magnet is falling through this plastic cylinder, there is no eddy current formation, no wastage of energy. It falls like free fall in the gravity. In the second case, the magnet is in free fall. But in the first case, there is a lagging for the magnet because of the wastage of energy in the form of heat, eddy current formation. Okay, this is the concept. Magnet takes longer time to cross aluminum pipe. That is correct. Because of eddy current formation, some energy wastage, so it takes more time. Okay. Magnet takes longer time to cross plastic pipe. That is incorrect. Eddy currents are generated in aluminum pipe but not in plastic. That is the answer. That is why option A. That's why option A. Both A and C are correct. Answer is option D. Clear? Okay. The next. Which of the following statement is wrong? A. In AC generator, when flux through coil is maximum, EMF induced is maximum. Yeah. This is to be calculated. Consider the field intensity set into the plane of the board as shown. Suppose. Okay. An AC generator is designed such that the field intensity directed into the plane. Okay. Now, an armature coil is set here, initially in this orientation. See. Now, in this context, the field intensity vector B directed into and the area vector A also directed into. Theta, the angle between those vectors is 0. So, the flux phi is BA cos theta is maximum, right? BA cos theta is maximum in this orientation. Okay. Yeah. And the EMF induced we have E is equal to E max into sin theta. The induced EMF is E max into sine theta. But theta here now is 0, sine 0, 0, and the EMF induced in this orientation is 0. When flux is maximum, EMF is 0. Okay, and when the coil turns by 90 degree, now flux becomes 0 and EMF becomes maximum. Clear? Now what about the options? In AC generator, when flux through coil is maximum, EMF induced is minimum. Okay, that is correct. In this orientation, flux is maximum, EMF induced is minimum. Okay. Now, maximum EMF is induced when plane of coil is parallel to magnetic field, plane of the coil. Okay. Maximum EMF is induced when? See, now the EMF induced is minimum. When it turns by 90 degree, now the plane of the coil is parallel to the field lines. Okay, plane of the coil parallel to the field lines. Now the EMF is maximum. So this statement is true. Okay, we have to select the wrong statement only, right? See, the EMF induced changes periodically with time if coil is rotated at uniform rate. Okay. See, what about this theta? Theta is omega t. Theta is omega t. That is, this EMF induced is E max into sine omega t. Sine omega t. Clear? So this EMF induced depends on the time. Even though it's rotating with a constant rate, if omega is constant but time changes, so EMF changing. So this statement is also true, option C. Finally, the frequency of rotation of armature coil is 60 Hz in India. That is incorrect. In India, it is 50 Hz. In India, okay, it is 50 Hz. The generators are set such that the frequency of the armature coil is 50 Hz. So this is incorrect statement. The answer is option D. Yeah. Next one. A pair of adjacent coils has mutual inductance of 1.5 Henry. A pair of adjacent coils has mutual inductance 1.5 Henry. If the current in one coil changes from 0 to 10 ampere. Clear? The current in one coil changes di, okay, or delta I. The current changes. Suppose I am taking as delta I. Delta I. 0 to 10 ampere. So what the change is? 10 ampere. The change in current is 10 ampere. In 0.5 second, the time interval for this change is 0.5 second. Okay. The rate of change of flux linkage with other coil is flux linkage with other coil. Okay. We have the flux, the magnetic flux of the other coil phi is equal to mutual inductance into current. Okay, flux of one coil is equal to mutual inductance into current through the other coil. Current through the other coil. Okay, okay. Then what about the rate of change of flux linkage is delta phi by delta t. Delta phi by delta t is equal to m into delta I by delta t, very direct. Clear? M is given 1.5. Yeah. Delta I is given 10. Delta t is given 0.5. Okay. Okay, yeah, 0.5 is 1 by 2, 2 to the numerator, 10 into 2, that is 20. Okay, 20 into 1.5, that is 30. 30 is the answer. Okay, yeah. So the rate of change of flux, okay, the rate of change of flux is equal to the EMF induced. EMF induced. So delta phi by delta t has the SI unit as that of the EMF or potential or voltage. So 30 volt is the answer of the question, option B. Clear? Very easy. The final one. A circular coil is being deformed into a narrow straight wire at a regular stretch. Then see, this is a circular coil is being deformed into a narrow straight wire at a regular stretch. Then what's happening? For a particular perimeter, a circle has maximum area. We studied it. Okay, for a particular perimeter, a circle has maximum area. So a circle has minimum area, isn't it? That's the correct one. For a particular perimeter which has the minimum area is for a circle. Yeah. Now, what is happening in this case is the area is increasing. Initially, it was circular shape. It was in circular shape. Now, it is stretched into a narrow one. So, what's happening to the area? The area is increasing. Okay, that's the point. Area is increasing. As area increases, the flux, magnetic flux is increasing. Magnetic flux is increasing. Okay, yeah. As magnetic flux increases, there is change in magnetic flux so that the EMF will be induced. EMF will be induced. Okay. EMF will be induced. This is Faraday's law. Okay. Yes. The induced EMF will resist the change of magnetic flux. That is Lenz's law. Okay. EMF will be induced so that induced current will be there. The current flows in such a way that it opposes the further change. Okay. What is happening to the flux here? The flux is increasing. Okay, so the current induced opposes the further change, means the current induced opposes the increase in flux. Okay, so the induced current tries to reduce the flux, isn't it? The induced current tries to reduce the flux because here the flux is increasing. Okay, if the flux was decreasing, then the induced current will try to increase the flux. That's the nature, and that is what the definition of Lenz's law studied it. Okay. So here the field intensity directed outward. Okay, dots outward. Okay. And the area is increasing so that the flux is increasing. So the current will be induced, which will oppose the increase in flux. So that the current will produce a magnetic field intensity directed into the plane. Okay, then what will be the direction of induced current? See, if the direction of induced current is in the clockwise direction, then what will be the direction of field intensity? If induced current is in the clockwise direction, then the field intensity will be directed into the plane. Okay, right hand thumb rule. Okay, induced current in the clockwise, then the field intensity into the plane. Clear? Means the field intensity opposing the outward field. Then it tries to reduce the flux. You understood? Means here induced current will be directed in the clockwise direction only. This is a very good question, understanding the concept of Lenz's law. Okay. First of all, circular shape, minimum area. Then into a narrow stretch means area increasing. Area increasing means flux increasing, EMF induced, current induced. Current induced opposes the change in flux. So current induced will produce a magnetic field intensity into the plane. Since here the external field intensity outward, so the induced EMF will produce a magnetic field intensity into the plane. Into the plane means the induced current should be in which direction? It should be in clockwise direction. Clockwise. Clear? Very good. Now the options. The direction of induced current is in clockwise direction. That is the first one. That is correct. Okay. The direction of induced current is anti-clockwise. That is incorrect. Contradictory statements. See, magnetic flux through coil decreases. That is incorrect. Magnetic flux through the coil is increasing due to the increase in the area. You know, flux is B dot A. B remains constant here. A is increasing, so flux increasing. That's the point. The amount of charge flowing in the coil depends on time. Induced charge is not depending on the time. We know. What about the induced charge? Studied it. Induced charge, you know, delta Q or dQ, I can write dQ. Induced charge, dQ is equal to I into dt, isn't it? Current into time interval, I into dt. And what is I is equal to EMF divided by resistance into dt. Okay. And what is EMF induced is? EMF induced is d phi by dt. EMF induced is d phi by dt. What happens? dt is cancelled. dt is cancelled. What is the induced charge dq is equal to d phi divided by resistance. The change in flux divided by resistance. So the induced charge is not depending upon the time interval. Okay, d phi by r is the induced charge. Okay, so this statement is also incorrect. The amount of charge flowing in coil depends on time is incorrect. The correct answer is option A. Hope you understood the concepts very well. Okay, now is the time to wind up this discussion. Study well. See you. Thank you.